Welcome back everyone to this discussion of regularization for linear regression. In particular, in this lecture, we're going to discuss data setup. So we just learned about things like cross-validation, standardizing our data, scaling it, and also just regularization in general. Coming up after this, we're going to discuss three main methods of regularization for linear regression, and that is ridge regression, lasso regression, and then elastic net. But in order to fairly compare all three regularization methods that relate to linear regression, what we want to do is make sure we're operating on the same set of training data and test data. That way we can fairly evaluate and compare all their performance metrics. So let's go ahead and head over to the notebook and get our data set up in order to then dive into both theory and intuition of the regularization methods and then also their Python and scikit-learn implementation. I'm going to head over. All right, here I am at the Jupyter Notebook. I've gone ahead and imported NumPy, Pandas, PD, Matplotlib.pyplot, and Seaborn as SNS. What our main idea here is just to set up our data set. That way we can immediately jump into regularization. We're going to be working with the same advertising data set as before. That way you can feel free to compare performance across many methods, including linear regression, polynomial regression, and then also the expansion of regularization on something like a polynomial feature set. So we will say pd.readCSV, and we're going to read in the advertising.csv file, and then we'll split it up into the features that we're already familiar with. We can do this by saying x is equal to df drop sales along axis equal to 1, and then y is going to be equal to just the sales column. So now I have my feature set as well as my label. The next step is to, if you want, create the polynomial feature set. So this will expand later on when we use regularization on the polynomial feature set. Right now we only have 3 features, but we can create degrees of those features as well as create the interaction terms. And that's really a separate process from doing something like regularization. It's essentially more akin to feature engineering and expanding that data set. So what we'll do here is just as before, we'll say from scikit-learn, pre-processing, import, we'll discuss here polynomial features, create the polynomial converter just as we did before. So we can say something like polynomial converter is equal to polynomial features, and this is where you can choose the degree. You can either choose a second degree or third degree. Back in the polynomial regression lecture, we went ahead and chose a third degree polynomial, so let's just go ahead and choose it now. Same thing, and then we won't include that bias term, it's just going to be a bunch of ones. So we'll say include bias is equal to false. Go ahead and run that. Now that we've created the converter, let's convert for the polynomial feature set. So we'll say poly underscore features is equal to, and then grab your polynomial converter, and then do a fit transform on the entire data set. So now if you take a look at X shape, it should be, whoops, if you look at poly feature shape actually, not X. X is the original, 3 features by 200 rows. Check the shape of the poly features. You have now 19 features because that includes not just the original terms, but also interaction terms, and then interaction terms between things like the higher degree terms. So the second power to the third power and so on. Okay, now let's go ahead and do a train test split, and then we'll go ahead and scale the data. And I know we discussed cross-validation. Later on when we discuss how to actually tune the parameters of the regularization methods, we'll dive back into cross-validation. For right now though, we can safely do a normal train test split. So we'll say from scikit-learn dot model selection, import the train test split, and then what I like to do, as you probably know by now, is just scroll down the documentation and then go ahead and grab this X train, Y train, etc. That way you make sure the tuple unpacking works correctly. And we're going to use the same random state and test size that we've been using, which is a test size of 30% of the data and a random state of 101 in order to just fairly compare all the models across everything we've done so far. And whoops, we want to make sure that we pass in our poly feature, not our X there. So we will say train test split poly features. So run that again, make sure you do that correctly. Again, we want to make sure we're passing in poly features with 19 different features for our X train and X test. We can confirm this by saying X train shape. You can see here xtrain is now 140 rows, 70% of the data, but it's still the 19 columns. Okay, so again, train test split, pass in your poly features, and then your y label. So now that that is ready to go, what we're going to do is scale the data. To scale the data, it's also coming from scikit-learn's preprocessing library. We'll say from scikit-learn, preprocessing, import standard scalar. Notice I'm just using tab to autocomplete here. And then we create the scalar. Very similar to creating the polynomial features or even just a linear regression model, you just create an instance of standard scalar. And hopefully now you can see why it's so nice. The framework for scikit-learn is so uniform across multiple functions and multiple classes. So now you have this instance of the scalar. And as we previously discussed, pretty much any standardization or any normalization or scaling method is going to scale based off mean values or standard deviation values. And in that case, we have to think, what mean or standard deviation should it be calculating? Should it be calculating the mean of everything that we have in the X set or the polynomial feature set? Or should it only be calculating the mean or standard deviation off the training set? And this is where beginners in machine learning often make a crucial mistake. We do not want to assume any information from the test set. Otherwise, that would result in data leakage, as we previously discussed. So since we don't want any information leaking from the test set, what we do for the scalar, in order to calculate things like a standard deviation or mean, it needs to be fit to a data set, but we should only fit it to the training set. That way we get no information coming in from the test set. Once it's fit to the training set, then we can create the scaled versions. So we'll say xtrain is then going to be equal to scalar transform the original xtrain. And then we'll do the same for xtest. Scalar transform xtest. Keep in mind, some people like to actually assign these different variables just to keep track. They sometimes like to call it scaled xtrain and scaled xtest. For simplicity, we'll just keep it as xtrain and xtest and overwrite the original ones. But just keep that in mind. Sometimes it's a little easier to track everything if you retain your original xtrain and then have a scaled version of it. But to quickly show what xtrain now looks like, at least the range, let's grab the first row off xtrain. You'll notice all the values are quite small now. Even though for the original one, if we take a look at poly features, and let's just take a look at the first row of poly features, notice the range here for some of these features. You're looking at things like 1.21 times 10 to the power of 7. So you have very large numbers here, but now that they're all scaled down to pretty much the same range, we can fairly evaluate those coefficients from one feature to the other, even though the original features were now in terms of things like $squared. So it helps us out a lot to scale this data, especially when we're considering things like coefficients and performance. Okay, so now notice again what we did here is we only fit to the training data to prevent any leakage from the test set. Now that we have our xtrain and xtest, as well as our ytrain and ytest ready to go, we can now dive into the regularization methods. I'll see you at the next lecture where we begin to discuss regularization methods with ridge regression theory.